Welcome to Methods in Biostatistics. Today, we are going to explore the very foundation of all biological research, qualitative and quantitative data. Whether you are tracking genetic traits in fruit flies or measuring the effects of a new drug, every single piece of information you collect falls into one of these two categories. Understanding how to classify your data is the crucial first step before any mathematical analysis can begin. Let us dive in and discover how we make sense of the biological world through data. To understand the two worlds of data, imagine you are a doctor walking into a busy clinic full of patients. As you interact with them, you gather two very different types of information. First, you notice descriptive traits, like their eye color, their blood type, or whether their pain is mild, moderate, or severe. These labels tell you about the quality of the patient's condition. Second, you use instruments to measure their exact height, weight, or blood pressure. These exact numbers tell you a specific quantity. In biostatistics, we divide all collected information into these two distinct buckets. Now that we have seen the clinic analogy, let us formally define our first bucket, qualitative data. Also known as categorical data, this consists of values that describe an attribute, a category, or a label. Because these values represent distinct groups rather than numerical magnitudes, they do not behave like regular numbers. You cannot meaningfully add, subtract, or average qualitative data. For example, trying to calculate the average of blood types A, B, and O makes absolutely no logical sense. This data simply tells us what category a subject belongs to. Building on our understanding of categorical labels, we can divide qualitative data even further into two specific subtypes, nominal and ordinal. Nominal data includes categories that have no natural order or ranking. Blood types are a perfect example. Type A is not mathematically greater or lesser than type O. On the other hand, ordinal data involves categories that do have a natural, logical order. Think of a pain scale ranging from mild to moderate to severe. While we still cannot calculate a true average, the inherent ranking gives us more structure than nominal data. Moving on from categories, let us look at our second major bucket, quantitative data. Also known as numerical data, this consists of values that represent measurable or countable quantities. Unlike qualitative labels, these are true numerical magnitudes. Because they are real numbers, mathematical operations like calculating an average or a standard deviation make perfect logical sense. For instance, measuring cholesterol levels in milligrams per deciliter gives us exact quantities that we can add, subtract, and analyze using powerful mathematical tools to find trends in our biological research. Just as we subdivided qualitative data, we can also split quantitative data into two distinct types, discrete and continuous. Discrete data involves quantities that are counted as whole numbers. You can't have half a cell, so counting the number of cells in a sample gives you discrete whole values. Continuous data, however, involves measurements that can be broken down into infinitely smaller decimal fractions. When you measure a patient's height or weight, the exact value depends on the precision of your instrument. Both types are numerical, but they are recorded differently. You might be wondering why we need to obsess over classifying data into these specific categories before we even do any math. The reason is critical. The type of data you have strictly dictates the statistical tools you are allowed to use. If you try to average qualitative blood types, the result is nonsense. Conversely, if you treat exact quantitative blood pressure measurements as mere categories, you throw away valuable mathematical precision. In real-world medical research, choosing the wrong statistical test can lead to false conclusions, which could ultimately harm patients. Classification is your foundational bedrock. Now that we understand why classification matters, let us look at how we mathematically summarize qualitative data. Since we cannot calculate a mean for categories, we calculate a proportion instead. This formula tells us the fraction of a group that shares a specific trait. The symbol P represents the proportion. The symbol F represents the frequency, which is simply the count of individuals belonging to that category. Finally, N represents the total sample size. If the frequency F increases while the total sample N stays the same, the proportion P will increase, meaning that category is becoming more dominant. Before we move on, let us see this proportion formula in action with a concrete example. A researcher collects blood type data from a small clinic. We're given a total of 50 patients, and we know that 15 of them have type O blood. We need to find the proportion and express it as a percentage. Because blood type is qualitative, we use our proportion formula. We plug in our frequency of 15 and divide by our total sample size of 50. This gives a decimal of 0.30. Multiplying by 100 gives us 30%. Physically, this means there is a 30% chance a randomly selected patient has type O blood. Having successfully summarized qualitative data, we now turn to quantitative data. Because these values are true numbers, we can find their center of gravity by calculating the arithmetic mean. The symbol x bar represents this sample mean. The Greek letter sigma is a mathematical command telling us to add things up. The term x sub I represents each individual numerical measurement in our dataset, and n is the total number of measurements. Conceptually, you just add up all your individual measurements and divide by the total count. If any individual measurement increases, the overall sum increases, which in turn causes the mean to increase. Let us apply our mean formula to a real-world quantitative scenario. A nurse measures the resting heart rate of 5 different patients. The recorded values are 70, 75, 80, 65, and 90 beats per minute. We need to calculate the mean heart rate. Because heart rate is measured in exact numerical units, it is quantitative, allowing us to use addition and division. We set up our formula, placing the sum of our 5 specific measurements in the numerator and the total count of 5 in the denominator. Adding the rates gives a total of 380. Dividing by 5 yields 76. This single number helps the nurse quickly understand the group's general cardiovascular health. Now that we have calculated summaries for both types of data, let us look at this flowchart to visualize the entire landscape. At the very top, we start with all collected data. Following the left path, data can be qualitative or categorical, which further splits into nominal data with no order, like blood types, and ordinal data with a natural ranking, like a pain scale. Following the right path, data can be quantitative or numerical. This splits into discrete data, which we count in whole numbers, like cells, and continuous data, which we measure exactly, like height. This map guides your entire statistical journey. We have covered a lot of ground today, so let us reinforce the most important ideas. First, always remember that qualitative data gives you descriptive categories, while quantitative data gives you measurable, exact numbers. Second, Correctly identifying your data type is crucial because it strictly dictates which statistical tools you are allowed to use. Finally, we summarize qualitative data by looking at frequencies and proportions, whereas quantitative data allows us to calculate deep mathematical metrics like the arithmetic mean. By simply asking yourself whether you are counting categories or measuring exact amounts, you will always know the right path to take.